We restart. Do you hear me on Zoom? Yes, thank you. That was a broadcast. Maintenant, j'ai perdu. I mentioned the fact that with IPv6, it's better without mask. I mentioned that with IPv6, hosts will also have temporary addresses. Right. Why is that? Well, we have seen that with NAT last week. With NAT, when you surf the internet, your address, your IPv4 address is not visible. Only the IPv4 address of your home access point is visible. With IPv6, in principle, we don't use NAT, so the end user address is visible. So if we want to avoid this privacy problem, one solution is to use randomly assigned addresses. So Windows and Macintosh system do that. They will assign to your IPv6 machine a random address that they will change every few hours, so that somebody who gets information on you cannot recognize that it's you again. Of course, you can use cookies or other thing, but not by simply looking at the IPv6 address here. Of course, this has side effects. If you have addresses that change, there may be problems. For example, if you're communicating with a web server, and this server has established a session with you, a TLS session for security, for example, and then you change your IP address, we will see in the programming lab that everything breaks when you do that. When you have a TCP connection between two endpoints, you cannot change the IP address of one of the endpoints. You have to break the connection and open a new connection first. So this is taken care of by keeping old addresses as long as they are in use. So if you keep a session during a very long period of time with a server, the temporary address that was allocated to you at the time you connected that server will remain in operation, will remain valid. So your host will continue to respond to this address. But it will be called a deprecated address here. Deprecated address means an address that has been used some time ago and we continue to maintain because somebody is using it. But if I connect again to the same server, I will not use this address, I will use what is the current value of the address here. So fairly simple, fairly straightforward. The side effect is that, you should expect a host with IPv6 to have lots of IP addresses here, unlike what happens with IPv4. I'll skip that, that's obvious. A last little thing that is sometimes visible to us is what is called DHCP with prefix delegation and exclusion. If you're at home with your edge router, so your ADSL modem, that's the way we call it usually, for IPv6, you expect to receive from your operator not just one address, but a block of addresses here. We've discussed that already, and this is why we don't have NATs with IPv6, or we don't expect to use NATs with IPv6. There's a small subtle detail. It simplifies the job of your provider if the IP address of your ADSL modem and all the addresses that are in your home are in the same prefix. Why does that simplify the job of the provider? Well, because then you appear as only one prefix. So here, for example, this provider delegates this string /60 to Lisa, and the IP address of this end system of the router here belongs to this prefix, which means that in all routing tables, in all information that the provider has about Lisa, all it needs to know is this 60-bit prefix. The other way of doing would be you allocate to Lisa prefix, and the home router address, as visible on the provider network, is a different one. Doesn't fall in this prefix. In that case, your provider needs to have two blocks for you. One address that is your router here, needs to know how to go to this thing, and also needs to know how to go to the subnet that is allocated to you. But since the subnet for this router is always behind, for this provider is always behind this router, this gives two addresses that go to the same place. You avoid this, and practically that means you have a prefix that must be excluded. So for example, the 01 here must be excluded from all the subnets you give at home. So if you play with that at home with your router, you have to make sure you don't give to one of your systems the same subnet as is visible for the provider. As we mentioned, multiple addresses per interface are expected with IPv6. That will practically always occur. And then, of course, there are issues like if I start a socket program, if I connect to a web server, which source IP address should I use? It's a problem that we did not really have with IPv4, but which with IPv6, since you have many, you have to choose one. So there's not a single solution to that, but there are simple rules, like for example, if you connect to somebody and that somebody has a link local address, so an FEAT address here. So if if two guys in the same LAN talk together, if you connect to someone that has a link local address and it works, it means that guy is in the same subnet as you. So one of the rules is for such cases, you use your subnet, your link local address as source address here. So one of the rules is always use the link local address when you can, because it's more stable. It doesn't contain prefixes that need to be allocated by external mechanisms. Other than that, then there are different rules, and Windows and Mac do different things, but you should expect that there are multiple addresses. So when we do Wireshark, you have to be aware of that. We might see different addresses to the same host. It's quite normal. Another converse of this is, because one of the rules is use link local address as much as possible, a router that has multiple interfaces, or a host that also has multiple interfaces like Wi-Fi and Ethernet, cannot recognize from an address sometimes which interface it is on. If I give the global address by analyzing the prefix of the address, I can know which prefix it is on. So for example, in a routing table of a router like this one, if I see a destination address, a next hop address, which is for IPv4, this one, then I know I know on which interface it is, because this router knows that on its south interface, it is configured with this subnet. So if the next hop is this address, I don't need to give the interface number. But if I give only the link local address, like FEAT/:1, then the same address exists on two local area networks. So it doesn't allow me to know which system it is. It also doesn't allow me to know on which interface it is. So on Linux, this is solved by putting in the routing table the name of the interface, ETH0, ETH1, etc. On Windows, it is solved by adding %1, %2 to the address itself in the routing table. So you will see next hop is this address, FEAT:1, %2. It means on the second interface. Well, those are all the ugliness that we might see. Link local addresses are universally used in IPv6. They exist also in IPv4. We mentioned that already. It is this block, but they are typically much less used. In IPv4, we don't expect an interface to use multiple addresses, so they are used only if DHCP doesn't work, and also there was no manual configuration. So a quick question to check a few things, and then that will conclude the DHCP story. I close the poll. Try. Okay, I've lost the connection to the server. Perhaps there was a change of IPv6 addresses. Are you connected to the SpeakUp server? Yes. So it's me. Okay, let's move on. The correct answer is D. So this is all the configuration that an IP host expects to have. And of course, this is what a DHCP server will give, because the goal of a DHCP server is to give all the information that you need to have. If we use Slack instead, what do we obtain? I close the poll. Tick. With Slack, you will obtain a link local address, and if your router is present in the subnet, a global unicast address. So you will always obtain a link local address. What is missing here? What do you not get with Slack? Well, if you compare to the previous here, we need an IP address, a subnet mask. We will obtain that with Slack. The default gateway address, as we can guess, if a router gives us a prefix, then we will also get the address of this router as a default gateway. But this is missing. The DNS server address is not part of Slack, so Slack is incomplete. You don't have full configuration, you have only IP addresses, but in practice today, a host that doesn't have a DNS server name might not work. It might work if you use the Google server, that works for everybody, but that's one of the ugliness. So Slack is typically complemented with other mechanisms just to get the DNS address of the server. So you need something else, which is called stateless DHCP. So you can go to DHCP just to get the DNS address of the server. It's called stateless because then the answer that DHCP gives to you does not depend on you. Everybody gets the same answer. And the DNS server will not remember that it gave you that answer because it did not allocate any address to you. Or there are also mechanisms for routers that are present in the subnet. Routers are typically configured, so you can configure them to also give the DNS address. Voilà, so much about configuration. The last thing we will discuss about the IP layer is the TTL field and perhaps a few other fields. So one of the fields that exists in IPv4 and IPv6 header is called TTL or HL. TTL is the time to live. Hop limit is the correct naming, but probably most people still continue to call it time to live. So what is the problem? Why is it present? Well, the problem is to avoid loops. The basic idea of the internet, of IP, in fact, of the CCLAB network before it, the idea of datagram is that the model of the postcard. Every IP packet is like a postcard, contains an address, and the routers have routing tables that say where to send the packet. In a fully managed world, you could imagine that there is never a loop in the topology. There should not be loop. I mean, a packet should not be caught in a loop. But in the world of computers, we know things are complicated, so problems are never excluded. So you need to catch the error cases where that happens. You cannot entirely exclude that a loop exists. You can exist because there is an error in the routing protocols. That happens regularly. We'll see particularly at the scale of BGP. But more fundamentally, it occurs because changes you do to the routers cannot be instantaneous and done at the same time. If you change a route somewhere in the internet, which happens all the time, the routes are always changing, particularly in the global internet. Perhaps at the level of a company, of a place like EPFL, routes don't change that often, but still, every so and so the routes will change. And of course, what do you do when a route changes? You don't stop everything, you just write the new value in the table, and you do that in all the routers. That will be the topic of Lab 4 to see how this is done automatically. When this happens, you don't synchronize all the routers. You could do that. You could say, I send a beep, a bit like the train system in Switzerland. You say, I've changed the things here. There is a new value of the routing table. Only when you receive the beep, you make sure you move on to the next routing table. You could do that. That's very complicated. To make sure everybody does it at the same time, you need to have precision time protocol to make sure we compensate for the propagation delay and everything. We don't do that in the internet. Instead, we change the routes whenever we find a better route. And as a result, there might be temporary inconsistencies. An inconsistency might lead to loops. A thinks that a packet with a given destination address should be sent to B, and B thinks it should be sent to A. Perhaps A has the newest information, and B has the old information. So in a few seconds, B will not send it back to A, but during those seconds where A and B are inconsistent, there is a routing loop. Here I'm showing a space-time diagram of a routing loop. I'm showing time vertically and space horizontally. A packet is sent from A to B, so you see here we have a small propagation time and a long transmission time. Perhaps it's not one packet, but several packets. And then this packet is sent back to B. So if it's sent back immediately, you see that a single packet, in fact, keeps the channel busy. Practically always in this case here. If the propagation time is larger, it will be less bad. There will be empty times, but still, transient loops may have the effect of destroying the line here. So even if there is only one subnet in the world that causes the problem of the loop, and the rest of the routing table is perfectly okay. If there is one packet that happens to be caught in the loop, then the line is down here. So it's a severe problem. It happens once in a while, but what we want to do is to limit the time during which it occurs here automatically. And this is taken care of by what was called a time to live. So time to live was originally really a time. So it was a time in seconds, which gives you an idea of how the network was at the time this was done. So we would accept that a packet lives in the internet for 20 seconds, for example, and we say after 20 seconds, it's a bit long. Of course, today that's ridiculous. A packet that has been in the network for more than a fraction of a second is probably already a backlogged packet. So it was a time. Today, it is no longer, it is still called time to live with IPv4, but what it really is a hop limit. Hop limit means the number of intermediate systems that it can go through. In principle, the current standard says at the source, you put a value of 64. And then every system that forwards the packet, every router, not every bridge, but every router that forwards the packet and sees the IP header will decrement it by 1. So we hope that the diameter of the internet today is less than 64, which is true today. In fact, it is well below 64. There is a small history that says when Windows implemented TCP-IP for the first time in a commercial deployment, which was in '95, they put 32 into by the default value was 32. And the first demos of the sales representative of Windows did not work because in Europe, when they were trying to connect to California, there was more than 32 hops here. The number of hops at the beginning of the internet were much larger. Now, the backbone of the internet has tended to collapse into very, very high speed backbone. So the number of hops is typically, in the worst case, not more than 30. And you've seen that when you've done some parts of Lab 0 with trace route. You see how many hops a packet goes through. So this is a limit on the number of hops that a packet can go through. So with traceroute, we sometimes find 20, 30, not more. By the way, this is how traceroute works. Traceroute sends a series of packets using UDP with increasing TTL. So it starts with TTL1. So you do a traceroute to Facebook. Then with TTL1, what happens? If Facebook is online with you, which means probably you work at Facebook and you're in the data center, this packet will be received. Otherwise, it will not be received. It will go on its way to Facebook. It will be received by your default router. The default router will decrement the value. We'll say, oh, it's 1. If I decrement it, it becomes 0, so I have to kill it. So the default router will kill the packet. And if the router is cooperative, when you kill an IP packet because TTL exhausted, you send an error message back to the source using ICMP, which is the protocol used for managing the IP layer. So when we do that, here the different routers of EPFL send back error messages, and the traceroute program will display the names of the router. How does it display the name of the router? Well, the routers don't give their name. They just send an an error message. What your host knows is the source address of the router that sent it. It will go to the DNS to do what is called a reverse mapping, find the name that corresponds to this address. So this here is a recreation of the traceroute software in your machine. It's not something that was visible in the packets. So in that case here, we see all the hops here. Many of you had problems doing that when we use IPv6 in the lab using Miredo, for example. We will see a bit later that Miredo uses tunnels. So Miredo puts the IP packet inside the IPv6 packet inside an IPv4 packet. In that case, of course, the IPv4 hops are not visible, the IPv6 header. In the worst case, if a Miredo host talks to another Miredo host, they will establish an IP tunnel directly from A to B. So from the terminology that we use, they are on link. So the TTL will not be decremented, and you will not see the traceroute. The traceroute will say, well, I'm directly connected to the destination. Also here, I was lucky. All the systems responded. Some of them don't have names. Those are typically routers, so not all routers have names. We can look up in the internet to see this IPv6 prefix to see to which company it belongs, probably Google. And all routers responded with an ICMP reply, error message. Many routers don't. In particular, if you go to inside routers that are inside the companies, if you go to IBM, for example, you will see stars. That means this traceroute program tried with TTL 10, for example, and then nothing came back. So the program will try again with 11 and will display stars instead. So this is the TTL or hop limit field. There are other fields in the IP header. One of them we will discuss a bit later. It's type of service and explicit congestion notification. So those are bits that are used to classify traffic. They are used in the internet, so the ECN bits are used. We will talk about it when we talk of congestion control. The other bits are used only in corporate networks. For example, at EPFL, we use the telephone system of EPFL is on the intranet of EPFL. We no longer have a set of switches just for telephony like we had 10 years ago. So telephone is just one IP application, but voice over IP requires a very low delay. If you want that it looks really like telephone, the delays of telephony are within 20, 30 milliseconds. If it becomes above, you see it's not IP telephony, but it's Skype or Zoom or things like this, where the delays are typically longer. And you may want to give priority to telephone. You may also want to give priority to Zoom, for example. I don't think EPFL does it, although I'm not sure. But certainly companies like AT&T, when they use their own, they deploy their own video conferencing services, they give a high priority to this traffic so that if there is a huge surge of web server traffic somewhere, it will not cause congestion to this traffic. So how this is done is that the routers will manage different queues. They will queue in different systems, in different buffers, the traffic that has a priority with the other traffic, the best effort traffic. And if there is congestion, then the congestion in one class cannot affect the other one. We'll talk about that when we discuss traffic control in the module that goes with Lab 5 here. Well, other things that we have discussed, and that's all I'll discuss about this slide. So let's conclude this part on IP with one little quiz. What happens when a host generates a packet with hop limit equal 1, or TTL1 if it's IPv6? It's what? I close in a few seconds. And the majority is right, as often. This packet will never be forwarded by a router because it has a hop limit 1. So the rules are you decrement the hop limit. When it becomes 0, the packet should die. So if you receive a packet 1, if you're the final destination, that's fine, you keep it. But if you have to forward it further, you delete, you destroy it, you drop it. For routers, because routers are devices that look at the IP headers. Bridges don't look at the IP headers, in principle. You can cheat, but if you don't cheat, a bridge looks only at the MAC header. That's, in some sense, the definition of a bridge. So this loop and TTL story will not be, has to be taken account for differently when we have bridges. So the TTL will not prevent loops with bridges. We'll talk next week about how we do prevent loops and problems with bridges. Voila. So we have covered practically everything, but not all, of the IP layer. We've seen that IP is built on two principles, one IP address per interface and longest prefix match. And second prefix, inside subnet, you go directly to the host. And in order to go directly, you need to find the MAC address, which you do with ARP or NDP. We've discussed NATs that came as an afterthought, but are so widely deployed that they play an important role in today's internet. And we've discussed DHCP and TTL or hop limit. We will see a bit later other topics, in particular things like fragmentation, tunnels, things that are also important, but that are, or proxy ARP, that are deviations from the architecture. So we'll start with a clean story. We did a few deviations already, like the NAT. We will try to do as few as possible, at least in the first part. So now we move on to the next topic, which is the MAC layer. Okay, this doesn't go away. Here we are. The MAC layer, we've already gone through it, we've seen the MAC addresses, we've discussed it a bit. Now let's go to the complete story that will help us understand why it is the way it is today. This diagram is illustrating, that's a patch panel. If you go to the basement of EPFL and open, or in some corridors, you open the cupboards that are in the corridor, you will see big racks of cables. This is where all the cables for all the Ethernet, and here in this room, there are probably 1, 2, 3 base stations that are connected to Ethernet cables. Those cables go somewhere. They go to things like this. So the primary goal of the MAC layer is to take care of the cables, and if possible, avoid them with Wi-Fi, like we do in this room here. We use Wi-Fi, which is a very elegant way of avoiding cable. But the true problem is interconnection at the local scale, which means cabling things together. MAC, which stands for Medium Access Control. I think on Moodle and in the chat group, there were questions. We also use the word on-link, so you will see also the link layer as a synonym. Today they are synonyms, so link layer, MAC layer are synonyms. And we will see why. Medium access control is because the Ethernet today should not be called MAC. There is no shared medium on Ethernet today. It's just like routers, except it switches. So it's the same hardware, just the forwarding algorithm that is different. But it's still called MAC, and here is why. At the beginning, this was Ethernet. The first Ethernet was like this. You take a coax cable, like a TV distribution cable, and you connect the computers directly to the cables here. When I was a student, this was the Ethernet that was in my university. You would see. Of course, there were not many computers, but still, I'm not so old, no, I'm not so young either. So there were more than a few mainframes. So you had a few hundreds of computers in a campus, and the computers were connected to a shared cable. There was an alternative to that, which was to connect the computer to the telephone system. And then you would have a point-to-point cable from every computer to a telephone system on which you would put a modem, and then it's what we have today with the Ethernet, which is using switches. But the very first things were not like this. Of course, today, we don't do that anymore. There are too many drawbacks. We'll discuss some of them. But this is exactly what we still have in other more modern equipment, like Wi-Fi, the cellular networks, Bluetooth, also power line communication is of the same thing. So if you use power line communication to distribute the internet into your house, which is typically what you do when you have problems with the penetration of Wi-Fi because you want to go from one floor to the next, for example, and it doesn't go well through thick concrete floors, then you use the electric cable as a medium, and then you share them because, of course, the cables are whatever they are. You connect to the electric socket, and then multiple devices can go here. So this is the environment. You have one cable or one radio channel, which from the practical point of view is very different, but from the protocol viewpoint is the same. And the problem is, if several systems talk together, then there is a collision. If A sends a packet, but B sends a packet at the same time, then the signal on the wires will add up. If one signal is much stronger than the other, and the coding system on the line or on the medium is very robust, then you might treat the other one as noise, and you might be able to decode. But if the signal levels are about the same, it will just create garbage. It creates what is called a collision. You cannot decode neither A nor B here. So the problem is that, how can we decode a signal when there is a collision here? With today's technology, if some of you take the course on mobile communication by Bixio Remoldi, for example, you will see that there are mechanisms for joint decoding. You can adjust, you should not be stupid. When A sends something, you can adjust the level of coding to make sure if another person is talking at the same time, perhaps you code with more redundancy, you become more robust to other signals that you may then treat as collisions. That's one way of doing it. There's even more radical ways, which says, we assume already at the beginning when I receive a signal that multiple people are talking, and I try to decode. This can be done using, for example, the 3G networks do that using what is called CDMA, code division multiplexing. The idea is that if you have in the same room somebody speaking English and somebody speaking French, if you tune to French, you will hear it, and the English speaking will just appear as background noise. If two people are speaking in French, that creates more interference because the processing is looking for words and not just decoding in an abstract sense. So this can be done, but this is fairly sophisticated and is done typically in cellular networks. In networks that we use in computer networks like Wi-Fi, power line communication, etc., we use mutual exclusion. Mutual exclusion means we prevent collision. We say only one system should talk at a time. So we prevent that from happening. This is what happens on Wi-Fi. We have these Wi-Fi's antennas. Many people can have the impression we're all talking at the same time, but we're not. At the time scale of Wi-Fi packets, only one Wi-Fi packet is received by any of the base stations at a given point in time. So that is called, in distributed system, a mutual exclusion protocol. Only one system can talk at a time. Of course, that's very easy to do in centralized systems. If you have a central switch, everybody connects to the central switch. And if you want to prevent many from talking together, you can ask for a token or ask for a permission to talk. This is what we do in this room, for example, because there is a speaker, and if you have a question, you raise your hand. And some systems were like this. They are called polling systems. Some machine buses are like this. Sometimes you need first to ask permission on one special set of wires, and then the bus controller gives the word to allows one system to talk. The system of interrupts works in this way. But in networks, we don't do it in this way. This works only, this has a large overhead. If the propagation time is non-negligible, whenever you need to talk, you need first ask permission on a separate channel, then you receive the permission. If asking and receiving the permission takes time, then it's not efficient from a throughput viewpoint. Plus you need a separate channel, which is okay on the machine bus where you have plenty of wires sometimes, but here we want to be smarter. So we want in particular that there is no central component. So those 4 computers should be able to work on the wires without any special one taking the role of an arbiter. So MAC layer is a very rich topic. There are hundreds of different MAC layer protocols. They work more or less all according to a small number of principles. Some of them are purely deterministic. This is, for example, the CAN bus. In your car, you probably have a CAN bus to distribute the signals when you press a button to stop the radio, for example. There's a CAN bus that sends the signal to your radio. The CAN bus is also used for other control. This one uses a static schedule in time of frequency. So this is for industrial systems where the hosts are statically configured. It's not okay for an Ethernet network, but if you build a car, you build a number of devices, and perhaps there's one slot for your radio systems, but you don't expect somebody to create another slot for an alternative radio system, right? The only thing you can do is change the radio. So you have a static network with static number of hosts that can communicate, and you allocate rounds. With CAN, you say there is a time frame, for example, of 125 microseconds. During this 125 microsecond, this device has the first 10 microseconds and can use that. It's called time division multiple access, and it was used in 2G networks, cellular telephony. 2G was using this system. The CAN bus uses it also. So this is fairly primitive, works well, is very cheap, easy to do, and works well for small scale network or for historic old systems. An improvement of that, this is called deterministic in the sense that you can know exactly how much of the channel is allocated to every device. Another deterministic scheme is token passing. This was very popular in metropolitan area networks or alternatives to Ethernet. Every host takes a turn and passes a token to the next. This is has very nice stability properties, but is not very much used today. Instead, all systems that are used today are descendant of ALOA and CSMA that I will explain in a second. They are called random access. So random access, the idea is you don't try to pass a token or ask a permission or something. You try to be smart and infer whether sending now could generate a collision. And if there is a collision, don't do it. And the system is not perfect for reasons that will become obvious a bit later. If once in a while there is a collision, then you find a way to detect it and to repair it. So all systems use this. This is what is line in power line communication, in Wi-Fi, in even cellular network that use today CDMA or frequency division multiple access. In 4G networks use simply different frequencies, a very minuscule bands of frequencies, and when two packets are sent, they are never at the same time in the same cell on the same frequency. But still, to control this, you need a signaling channel. For example, when you join a new cell, or when you leave a cell, or when a new call is passed, and this uses also ALOA and CSMA that we will explain now. So random access. How does it work? ALOA is a Hawaiian word for hello. It's the Hawaiian pronunciation of hello. And believe it or not, the first radio networks were in the 70s in the Hawaiian Islands, where those are 5 different islands. So at that time, the computers were mainframes. So there was one mainframe here and 4 other mainframes, and they're trying to communicate together. There was one channel for the downlink going from the center to the remote, and one channel for the uplink here. Collisions could occur only on the uplink, because on the downlink, there's only one sender, which is the center. So there's only one sender, and there cannot be collisions, because the sender is not stupid. It serializes its sending. But the remotes can create collisions. For example, if remote on island 1 sends a packet to the center on the main island, if someone else sends at the same time, that could create a collision. So here's how ALOA works. That is the optimistic views of the 70s. You simply send a frame. So when you're a sender, you frame. And then you wait for an acknowledgement on the return channel. The return channel here is free of collision, so there's nothing to manage for the return channel. And if the acknowledgement comes, it's a confirmation that you could send your packet. So there was no collision, or if there was a collision, it was to your advantage. Your packet was stronger than the competing packet, so your packet made it. Otherwise, if it doesn't work, you detect that, like we've seen the stop and go protocol. You detect this by absence of ACK, and the ACK is, so you wait for some timeout. So if you try, if it doesn't work, you detect that it doesn't work because you've timed out. And then what do? You try again. You try again with a small caveat, you wait for a random time. Right? Why do you need to wait for a random time? Well, because if the collision was a true collision, A has sent, B has sent at the same time. If the timings are about the same, if both do the same algorithm and try at the same time, they will create a collision again. So you're in the deadlock, you will never get out of this deadlock, or it will take a very long time. So you randomize. This is ALOA. And believe it or not, it works fairly well, but of course is a bit primitive. It works well as long as the attempt rate is small. So analysis have been done with various assumptions. Up to 17% of utilization of the channel, it's an efficient way of doing it. 17% utilization means if the coding rate of this is, for example, 1 megabit per second, it works as long as the traffic from the remote to the center, the total traffic of all the remotes to the center is only 17% of 1 megabit per second. So it works well if nothing else is acceptable, but of course today we want better things. We're not happy with wasting 80% of the capacity due to inefficiencies. How this was improved, we will discover next week when we talk about the second part of the MAC protocol. Bonne semaine à tous.